Does that work? Hello, did that work?
So let's start now. I'm very sorry for all the technical issues.
No worries.
And so welcome everyone. Today our speaker is Leo Torres. So Leo currently is a postdoctoral researcher at Max Planck Institute for Mathematics and Sciences in Leipzig, Germany, in the group of Eugen Drost. He has his PhD in network science from the Network Science Institute at Northeastern University under the supervision of Tina Alice-Rad. So his research lies in the interaction of network science, complexity science, and mathematics. And he specializes in applying spectral methods to machine learning or data mining tasks on networks. So let's welcome Leo. Please feel free to start.
Thank you. Thank you very much for the introduction, for the invitation. Thank you everybody for being here. I understand that you can hear me and see my slides. So if you don't see them moving, let me know and we'll see what happens. All right, so my name is Leo. Thank you for coming. I would like to talk to you about today about this thing called X-centrality, node immunization, and also a little bit about something else called eigenvector localization. So at the end, I'm going to touch upon this topic of eigenvector localization, but be warned that this is very much a work in progress. So the last little bit is going to be a lot more scattered than the beginning of the talk, and I would very much like your feedback in the entire thing, but in particular at that last part. All right, so the research question for today is the following. What happens to the leading eigenvalue of the non-backtracking matrix of a graph when a node is removed from the graph? Once we develop a little bit of theory to answer this question, we're going to use this knowledge to define a centrality measure that we're then going to use for the task of node immunization. So in the context of a disease spreading over the network, you can think of removing a node as immunizing that node against the spread of disease. And of course, you need to choose which nodes you're going to remove depending on the centrality measure that we're going to develop in a second. So this is sort of the kind of ideas that I'm going to be thinking about. But first of all, before all of that, I want to convince you that you should, first of all, care about the non-backtracking matrix and its eigenvalues. So let me spend a few minutes talking about that first. So let me define it once and for all. Imagine you have a graph. So for me, graphs are the nicest kind of graphs. They're undirected, unweighted, simple, connected, finite graphs, right? The nicest kind of graph. So pick your favorite nice graph, and you're going to assume that it has m edges, okay? Now, the non-backtracking matrix of a graph can be understood as the transition matrix of a random walker that never traces backtracks. And so a backtrack is when you stand on a node, you go to a neighboring node, and then you go back to the node you just came from. So this going from node I to J back to I, that is a backtrack. So the non-backtracking matrix B basically tells you what steps are valid when trying to trace one of these walks. So, so to be a little bit more concrete, you have to imagine yourself being a random walker on this network, and let's say that you just went from the red node to the blue node, and then, like I said, you are not allowed to go back to the red node, right? But from blue, you can go to the green node or to the yellow node or to any other possibility. So in this case, the matrix is going to have a row corresponding to the oriented edge from red to blue. So even when the graph is undirected, the matrix is going to be indexed in the rows and columns by oriented edges, because the walker needs to remember the edge that it just traversed, but also the direction in which it just traversed that edge. So in this case, the matrix is going to have a row for the oriented edge from red to blue, and a column for the oriented edge from blue back to red, and the corresponding entry is going to be 0, because this entry corresponds to the backtrack red, blue, red. Whereas other entries corresponding to valid steps away from blue are going to have an entry equal to 1, right? So basically, this matrix tells you which steps are valid while avoiding backtracks. So this matrix has a ton of very interesting properties, a lot of applications. One of them, for example, is that you can more or less think of it as the adjacency matrix of the set of oriented edges of your graph, right? So just like the adjacency matrix, you can take the powers of this matrix and look at the elements of the powers of this matrix, and those elements are going to tell you the number of non-backtracking walks that start at one edge and end at another edge, right? So a non-backtracking walk is just a walk that never goes red, blue, red. So that is one of the properties that's interesting. One thing that also should be highlighted is that this matrix is square, but it is not symmetric. So its eigenvalues are in general complex numbers, which makes its analysis very, very difficult in many cases. So the reason why anybody would ever try to analyze a non-symmetric matrix is because, like I said, it has a lot of applications, both in theoretical mathematics as well as applications to network science. For example, it's related to something called the length of spectrum theory that I would love to talk about today, but I don't have much time for that. You can use it to define a method for graph distance, to embed your networks, to get the structural embeddings. You can use it also for more sort of complex network tasks, like community detection. For example, it's been shown that in certain regimes, you can use the non-backtracking matrix to perform community detection on the stochastic block model and get better performance than what you would otherwise get using the Laplacian in a spectral clustering sort of way. You can use it to define node centrality and so on and so forth. But today I want to focus on this particular application because it is known that the epidemic threshold of certain spreading dynamics, for example, the SIR or SIS models, the epidemic threshold theta is just the point in your parameter space after which the epidemic has a large chance, sorry, the spread has a large chance of becoming an epidemic, right? And it's known that the epidemic threshold theta can be approximated using 1 over the leading eigenvalue of the non-backtracking matrix. And
can I just ask? So yeah. in practice, how do you deal with leaves, right? So once you arrive on a leaf, the walker stops, right? Because it doesn't have anywhere to go. So in practice, if you have a graph with leaves, what is the canonical procedure to deal with that?
Yeah, that's a good question. So essentially, what you're saying, if you are trying to make a non-backtracking walk and you reach a node of degree 1, that's an absorbent state, right? You have to stay there. You cannot go back. So the way that this sort of materializes in the spectrum, at least of the matrix, is that if you have a graph and you add a node of degree 1, then the spectrum, the eigenvalues don't change. So the eigenvalues don't ever depend on the nodes of degree 1. What happens when you add a node of degree 1 is just you're adding to the multiplicity of the eigenvalue equal to 0. So if you're really interested in talking about the nodes of degree 1 using the non-backtracking matrix, then what you could do is look at the eigenvectors that are in the kernel. So the eigenvectors corresponding to the eigenvalue equal to 0, because the entire non-zero part of the spectrum doesn't care at all about those nodes. And you can think of, I mean, maybe that's a drawback, that's a disadvantage if your networks have a lot of nodes of degree 1. But the point is that I guess what these papers show here is that the epidemic threshold of these dynamics don't really depend so much on those nodes. They depend on the denser parts of the graph. Does that answer your question?
Yes, I think so. Thanks.
All right, good. Well, so the epidemic threshold theta is approximated 1 over the leading eigenvalue of the non-backtracking matrix, and this approximation is known to be better than the more common approximation that is 1 over the leading eigenvalue of the adjacency matrix. So usually it is my sense after years of studying this matrix that whenever it shows up, it seems to improve upon what we can do with other matrices in general. But so for now, let's think about this epidemic threshold that's related to the leading eigenvalue, because that leads us directly to our research question, like I said at the beginning. What happens to the leading eigenvalue and therefore to the epidemic threshold when you remove a node from the graph, when you immunize a node against the spread of disease? So let's do that. I'm going to tell you a little bit of how we go about doing the derivation for this. I'm going to give you the sense of what's going on here. The details, you can find them in the paper, right? So I'm going to start with this graph. I'm going to choose a node, arbitrary node C, that I'm going to call my target node. And I'm going to color the edges incident to my target node in yellow and the edges not incident to the target node in blue. And then I'm going to remove the node to get this graph, right? So this graph is going to be GC, and this graph after the removal is going to be G. So all of my symbols that contain the superscript C correspond to the graph before the removal that contains the target node C. All of the symbols that don't have the superscript don't have the node. So each of these graphs have their non-backtracking matrix. Each of those non-backtracking matrices has their leading eigenvalue. And what I'm interested in here is in trying to, whoops, sorry, I don't know what happened. It went all the way to the end. What I'm interested in here is in looking at trying to estimate the difference in the leading eigenvalue before and after I remove them. All right. So the way I'm going to do that is I'm going to take the graph before the removal with the target node. I'm going to look at its matrix. I'm going to order the rows and the columns so that all of those corresponding to blue edges form a block at the top left, and all of those corresponding to yellow edges form a block at the bottom right. And I'm going to name these blocks B, D, E, and F. So this is my big matrix BC. And what I want you to notice is that the top left block here in blue is exactly the non-backtracking matrix of the graph after the removal, because by definition, it only depends on the blue edges. With the other three blocks, I'm going to take them and I'm going to multiply them D times F times E, and I'm going to define this as my X matrix. You can work out the math and prove that this matrix also has entries equal to 0 or 1, and the 1 entries of this matrix indicate the existence of paths of length 4, of non-backtracking paths of length 4 of the type blue, yellow, yellow, blue. And these are very important because these are precisely those paths that go through the target node. Therefore, they are the paths that are destroyed when you remove the target node. So with all of these objects, I'm going to take my big matrix and I'm going to look at the characteristic polynomial. So if I find solutions for T, then those solutions are eigenvalues of the big matrix. And basically the derivation summarized can be said as follows. So you're going to apply a few tricks for determinant of block matrices. That's going to give you an expression like this. I'm going to focus on this term on the far right that depends on our matrix X that we defined earlier, and on the matrix Y, which is this matrix that depends on the matrix B here. So Y depends on my top left block, while X depends on all the other three blocks. So between Y and X here, I should have all of the information I need to try to estimate the solution. So I'm going to try to take this term and set that equal to 0. And then I'm going to essentially linearize this equation, applying some more tricks to find something like this, where the leading term is the trace of Y times X. The trace is nothing but the sum of the diagonal elements, so it looks like this. And from this sum, I'm going to take, once again, only the leading term, which looks like that, where here now X is my same matrix X. U1 and V1 are the principal eigenvectors of the matrix B. So they're the principal eigenvectors of the non-backtracking matrix after removing the node. And lambda 1 is the corresponding eigenvalue after removing the node. And I'm going to neglect some of these terms here. And I'm going to look at this right-hand side expression. I'm going to set that equal to 0, because if I solve that, then that will be an approximation of a solution of the equation that I started with. So I'm going to take this thing, I'm going to rearrange, and it looks like this. And now I win because this is a third-degree polynomial in the variable t, and as such, it has a closed form solution. So I can actually find a closed form solution for this, which is an approximation of the entire thing. But we can do a little better. We can do a little better because we can look at the constant term here. This is a term constant in t, right? And if you apply a little bit of calc 1 on this thing, you realize that if this constant term is large, then this difference right here is large. If the constant term is small, then the difference is small. And remember, what I'm interested in is precisely this difference, because once I solve for t, then this is going to be the leading or an approximation of the leading eigenvalue of the matrix before the removal minus the eigenvalue after the removal. So this term right here is precisely what I'm trying to estimate. And what I'm trying to say is that I don't even need to solve this equation. All I need to do to try to estimate how this behaves is look at how this behaves. So what we did, so let's take a step back. What we did is we took a graph, we chose a node, and we went through the entire derivation, and we found that this term that belongs to the node, is sort of associated to the node, is sort of predicting how much the node influences the amount of the eigenvalue, right? How much the node influences the eigenvalue. In other words, it's basically telling you how important it is. So this is a centrality measure, right? So we did what every network scientist worth their salt would have done with this thing. We defined a centrality measure out of it. We called it the X non-backtracking centrality. That's a mouthful, so let me tell you where the name comes from. The X comes because it is defined in terms of this bilinear form that depends from the matrix X. And now we called it the X non-backtracking centrality because, like I said at the beginning, the principal eigenvector of the non-backtracking matrix has already been used in the past to define a notion of centrality. And that's exactly what I have here. So V1 is the principal eigenvector of the non-backtracking matrix. So V1 already contains centrality measures. It contains what has been called in the past the non-backtracking centrality of the nodes in the network. So what this centrality is doing is it's taking the quantities of the non-backtracking centralities and it's recombining them via the bilinear form defined by the matrix X. So that's why it's the X non-backtracking centrality, because it's sort of a derived centrality measure from the standard non-backtracking centrality. And I'm going to come back to this in a second to try to elucidate what that means. Now, the problem here is that it's a little bit annoying to try to compute with this thing, because for every node, you have to go through the entire thing, compute an eigenvector and do this and that and so on. So what we did in the paper is we found that this X and B centrality is upper bounded by a term that is very much similar in its functional form. So this is vector X vector. This is the vector of all ones times X times the vector of all ones. Plus some other terms that can also be neglected. And we found that not only is this an upper bound, but we found that it follows the same behavior. So if this is large, then the difference is large. If it is small, then the difference is small. So we took this to be another derived centrality measure, which we call the X degree centrality. And in a second, I'm going to tell you why we called it the X degree centrality. But for now, I want to go back to the main research question: what happens to the leading eigenvalue of the non-backtracking matrix when the node is removed from the graph? It decreases by a quantity that is correlated to the X non-backtracking centrality of that node. How strong is a correlation? It is surprisingly very, very strong. This is far stronger than I was expecting. So every dot in this plot is a node chosen at random from graphs drawn from the stochastic block model. Vertical axis is the actual difference in the eigenvalue when removing this node. This is the X non-backtracking centrality of that node. You get a beautiful correlation that is actually even almost linear. I have no idea why it should be linear. The theory tells you that these should be correlated. It doesn't necessarily tell you that they should be linear. So I don't know why that happens. The same thing you see in other networks, in Barabashi-Albert networks. It's less beautifully linear, but it's still really strong. And before anybody asks, yes, all of these things are also correlated to degree, just no degree, which is the color in this plot. But when you measure the correlation between the drop in the eigenvalue and degree, that is always far less strong than the correlation between the drop in the eigenvalue and our centrality measure. So that is sort of the theory that went behind doing this. Let me highlight again, I'm hiding a lot of detail. Like I said at the beginning, the matrix is not symmetric. And that basically means that if you open a book of spectral graph theory, 90% of what you find cannot be applied to this matrix. You have to start from scratch most of the time. So in all of these derivations, in all of these terms that I'm neglecting and so on and so forth, there's quite a bit of more work that needs to be done there. And so on. But we get beautiful correlation, and we get a nice estimation of the actual drop in the eigenvalue, and we get our centrality measures out of it. So now let's talk about how to use this for the problem of node immunization. So by node immunization, I mean, like I said, generally just you have a graph, you want to increase the epidemic threshold of SIR models which is the same as decrease the eigenvalue as much as possible. For that, you're going to remove nodes one by one. And what the theory says is essentially you should choose nodes to remove based on their X centrality measures, the X degree or the X non-backtracking centrality. The problem, like I was hinting at before, is that that is very costly, right? Because if you have your network, you choose one node, the node is going to determine these blocks, the node is going to determine the matrix X. From that, you have to compute these eigenvectors, you have to compute this entire thing. And if you compute a different, if you choose a different node, you're gonna get a different blocks, different matrix, and different quantity here. So you have to look at the network, compute this entire thing for every single node, and then choose the one that has the largest centrality, and then do it again, and so on. And that's bad, right? So let's try to let's see how we can improve that. The way that we're going to do that is I'm going to look at this, but by linear form, which is written in matrix form. I'm going to write it in scalar form, and I'm going to find that it's nothing but this expression. So this expression is exactly the same as this. Let's see what it's saying. It is summing over all of the nodes. This A quantity is an element of the adjacency matrix. So it's summing over the neighbors of my target node C. And for each of them is taking the non-backtracking centrality of that node. It's squaring the entire sum, and then it's subtracting the sum of the squares of the non-backtracking centralities. And what this means is that I only need to compute one eigenvector. I only need to compute once the non-backtracking centralities of every node. And then to know the X non-backtracking centrality of each node, all I need to do is recombine the non-backtracking centralities of its neighbors using this quadratic function. That's a little bit better because that means that we don't need to compute the matrix X every time. I can just use the scalar formula, right? But it's still a little bit messy. So let's see what happens with X degree. Remember, X degree is just vector of all ones times X times vector of all ones. If you write it in the scalar form, you find that it looks like this. It is, of course, the same functional form, but now what you're aggregating here are these quantities D prime, which are the degree of my neighbor minus one, also called the X's degree sometimes in the literature. So the X degree of a node is just a quadratic recombination of the X's degrees of my neighbors. And that means that you can compute this one extremely fast because all you need to know is the degrees in all of your network and then how they change after you remove them. So that's what we're going to use for the task of node immunization. So I'm going to show you some results. It's going to be a table where the numbers tell you the average percentage drop in the eigenvalue after removing one node. So larger is better. I'm going to show you results for 4 different random graph models after removing 1%, 2%, or 3% nodes, always following different strategies. Those strategies are I'm going to remove nodes based on their degree. I'm going to remove nodes based on this NS centrality, which is called the net shield quantity in this paper, which is essentially derived in a very similar way what we have done, but it's targeting the leading eigenvalue of the adjacency matrix rather than the leading eigenvalue of the non-backtracking matrix. This CI quantity is called the collective influence, which is another centrality measure, also derived from the non-backtracking matrix, also depending on the excess degrees of my neighbors, but it has a different functional form. I'm going to use my X degree centrality. I'm going to use the standard non-backtracking centrality and also the X non-backtracking centrality. So that's what the table looks like. I want you to look at these 2 columns and realize, first of all, that the X non-backtracking centrality and the non-backtracking centrality usually almost always get exactly the same performance, like statistically significant, the same performance. And what that sort of means is that once you have access to the principal eigenvector, so the eigenvector containing the centralities, you're pretty much good to go. You don't need to recombine them. You can just use the eigenvector as it is. But then if you look at the X degree centrality, you will realize that it is doing better than all of the other baselines that we tried, statistically significantly better than the other baselines. And what that means is that this is sort of quote unquote the correct way of recombining the degrees of my neighbors to try to estimate the influence of the node into the eigenvalue. What I also want you to notice is the degree itself is already a very strong baseline on this task. And this is something that shouldn't come as a surprise, because we know that attacking networks based on degree is very effective, right? So from the word go, we are working with very, very small improvement margins here, but we're getting those margins to the point where, like I said in the paper, you will find that we found that these improvements, they are small, but they're statistically significantly better. And well, in the paper, you will also find similar results for real networks, for case studies in the case of networks that have a lot of nodes of degree 1, and so on and so forth. For now, I want to talk a little bit about the algorithm, because we found something that I found very interesting. So let's think about the algorithm for node immunization. This is exactly what you would expect. I'm not even going to go over it line by line, because it's exactly what you would expect. Compute the centralities of every node, get the largest one, remove it, update centralities, and do it again, right? What I want you to focus on is on this line right here, and in fact, on this data structure. So what I'm going to do is I'm going to compute the centralities of each node. I'm going to store those in some data structure. Usually you will use an array, or you would use some kind of hash table or map or dictionary or whatever you want to call it, right? Something that tells you this node corresponds to this centrality. That's it. All right. But let's see what we're doing over that data structure. What we're doing is, like I said, we're going to go over the data structure and take the node that has the maximum value. And then we're going to update some of the values that are in this data structure. In the particular case of my X degree centrality, remember, if I am a node, my X degree if I'm a node and I am removed from the graph, then the degrees of my neighbors is going to change. And therefore, the X degrees of my neighbors' neighbors is going to change, right? So if I remove one node from the graph, all I need to do is update the X degree centrality values of nodes that are 2 steps away from me. I don't need to update the entire network. All I need to update is a 2-step neighborhood away from me. Okay. So what we're doing with this data structure is we're storing a bunch of things. We're getting the maximum out of it, and then we're updating some of the values a certain number of times that is equal to the number of 2-hop neighbors. And that means that the algorithm can be implemented using different data structures. For example, if you use your array or your hash table or your dictionary or your map or whatever you want to call it, I'm going to use the name map. If you use a map, taking the maximum over this data structure is going to take time that is linear on the number of nodes, because you have to look at every single one of them. Though updating the values of that map is going to be, each update takes constant time, but you're performing a number of updates equal to the number of 2nd-hop neighbors. However, if you use something different, if you use something called an indexed priority queue or an IPQ, taking the maximum out of an IPQ takes logarithmic time, so it's faster than the map. But updating the IPQ takes also logarithmic time, so it's slower than the map. So whether you use the IPQ or the map is going to depend on the relative amount of times that you're performing taking the maximum versus updating a certain number of times. And the number of times that you update depends on the number of 2-hop neighbors. All of this is just to say that the data structure that you choose to implement this algorithm depends directly on the second moment of the degree distribution of your graph. So these are some basically wall clock runs of the algorithm. This is the IPQ version, the map version. This is time in minutes. The vertical axes are different. So the map is always slower, but it gets faster and faster and faster the more heterogeneous your degree distribution is. Essentially, so these are run over graphs that are sampled from the stochastic, not the stochastic model, from the configuration model that has been fed a degree sequence sampled from a power law degree distribution with the given gamma. So IPQ is very fast, but then if your gamma starts approaching 3 or more, the map version becomes better, because the relative amount of times that you're taking the updates versus taking the maximum sort of tips over and gives you the other option. And I was really interested when we found this, because well, first of all, because it's not a different algorithm, mind you, it's exactly the same algorithm, line by line. You can look at the reference implementation. It is the same function. It is the same code. What changes is the data structure used to execute that code. And I just wish there was more of this out there. I just wish that we were more able and interested in looking at how the efficiency of our algorithms depends on the underlying structure of the graph. So we did what we set out to do. Now let me tell you about a couple of observations that I had made at the time that this was published. Let's think about X degree again for a second. Remember, the X degree of a node C is a sum over my neighbors of the X's degrees combined in this quadratic way. All right. Now I want you to think about minus the variance of my neighbor's degrees, which kind of looks like this. And so you see that these are almost the same expression, except of course that the variance is normalized. All right. And that's sort of a nice sort of intuition about which nodes have large X degree or small X degree and so on. But so I'm going to come back to this in a second, because now it starts the last part of the talk. Like I said at the beginning, we're going to talk a little bit about eigenvector localization. So let me tell you what's eigenvector localization and go back to the X degree in a second. So eigenvector localization is the phenomenon by which we know, for example, if you look at the principal eigenvector of the adjacency matrix of this graph, well, everybody here will be able to tell me that the red node is going to have a large component there, so a large eigenvector centrality, and all of the other blue nodes are going to have a smaller eigenvector centrality. But what eigenvector localization says is that the red node has a huge amount of centrality, while all of the blue nodes have about the same centrality. And that is good and bad. It's good because if you're removing nodes one by one, then you want to know that there's one node that has a huge centrality and completely beats all of the others. But it's bad if, for example, you're trying to remove 2 nodes at a time. If you're trying to remove 2 nodes at a time and you look at this network, can you tell me which 2 nodes you would remove? I think everybody will remove the red node. And I also think that there are at least a couple of options for which of the blue nodes I would remove. So all things considered, extremely localized eigenvector, basically what I'm trying to say is that it ceases to be an effective way of ranking the smaller nodes. What I would like to have is an eigenvector that has large centrality for the red node, and then gradually smaller and smaller centralities for all of the other nodes. And I do not get that with a localized eigenvector. So it is known that the principal eigenvector of the adjacency matrix localizes on the red node, for example, on the star-like graphs that happen in your network. And in fact, this paper by Martin et al. Was sort of bringing this phenomenon up and pointing out that the principal eigenvector of the non-backtracking matrix doesn't localize in the same way. Then there was a bunch of other papers basically studying in which cases the principal eigenvector of the non-backtracking matrix actually does localize. And they showed, for example, that if you have a click or a near click or a motif that kind of looks like this, you will find a localized eigenvector of the non-backtracking matrix. And once again, that is perhaps less desirable in some cases. And what I had observed at the time of publishing this paper is that if you look at all of the red nodes, which are the nodes on which the non-backtracking matrix is localizing, their neighbors have degrees that are very similar, therefore low variance, therefore they have large X degree. So the nodes on which the eigenvector is localizing seem to have large X degree centrality. So I left the question open. When I published the paper, I left the question open, is there a way of relating X degree with eigenvector localization, and what does that mean, and how do we do this? So I'm going to tell you a bit of progress about that. That was sort of like the end of 2019, I think 2020. And so the rest, the following slides, some of the plots here have been plotted like last week. So this is very, very fresh, very much work in progress. So I don't really see how all of the pieces fit together yet, but this is the current update. And I'm trying to run a little bit because I think I'm running out of time. So anyway, I've been talking about localization in a very hand-wavy kind of way. So let me define it formally a little bit better. So if you have a vector x with components x, y, the localization of this vector is measured using a quantity called the IPR, or the inverse participation ratio, which is defined like this, which is a very, very strange formula if you ask me, because it contains these fourth powers, as well as the fourth power of the Euclidean norm of this vector. But that doesn't matter. What matters is that if you have a delocalized eigenvector, so you can think of a constant vector, all entries equal to 1, then the IPR is going to be in the order of 1 over n, where n is the dimensionality of the vector. Whereas if you have a localized vector, the IPR is going to be about a constant. For example, you can think of the extreme case where you have one component equal to 1 and all of the rest equal to 0. The IPR in that case is always 1. It doesn't depend on the dimensionality, right? So what we're trying to say here is that x degree, if you look at x degree, I'm going to manipulate this, this formula a little bit. I'm going to change variables, defining these y's as the root of the x's degrees. And now you see where this is going, because now I have these fourth powers. So if I normalize this thing and rearrange, I will find that the normalized version of x degree is nothing more than 1 minus the IPR of a vector whose entries are the roots of the x's degrees of my neighbors. And that's nice, because that means that I can relate x degree to localization. That low x degree means high localization of degrees around my neighbor. So basically, the thought process right now kind of looks like this. A node with low x degree means high IPR. High IPR means a localized non-backtracking eigenvector. A localized eigenvector has consequences on the percolation and epidemic thresholds of the network, and so on and so forth. Of course, things are a little bit messier than this, because what I have really is a low x degree means high IPR of degrees in my neighborhood, while what I need for a localized non-backtracking eigenvector is high IPR of the vector of non-backtracking centrality. But I also know that x degree and non-backtracking centrality are correlated because they are both centrality measures. They both sort of are trying to tell which nodes are important. So there may be sort of seems like there's a path forward in trying to relate these quantities. So what I'm going to try to do is I'm going to try to devise a random growth model to test the hypothesis of whether the x degree is related to the localization of the eigenvector, right? So, or under what conditions does one sort of influence the other? So we're going to grow a network in a very familiar way. At each node, at each time, I'm going to add a new node. This node is going to create R edges for a predetermined number R. For this purpose, I'm going to choose a node V with probability proportional to its x degree, not its degree, right? So this first part is very much reminiscent of preferential attachment, just based on x degree instead. And then remember, what I'm trying to do is increase localization as much as possible. I want to see a localized eigenvector, which is the same as saying decrease x degree as much as possible, or said another way, I want to increase the x degree of the chosen node as little as possible. And now, if you write it down and you look, if you look at the math, if you work it out, then you will be able to find that the way to increase x degree as little as possible is to connect to the R neighbors.
We have a question in the chat.
Oh yes. I have the chat here. Let's see. I'm curious why degree heterogeneity has such a strong effect on how well it's correlated with this. You can wait. Yeah, I can go back to that. Basically, you can use the X non-backtracking centrality to try to estimate the eigenvalue after removing a node, and it will give you. It's in the paper. It will give you relative error between 10 to the minus 3 and 10 to the minus 10. So it's a crazy thing where sometimes you remove a node and you predict the eigenvalue using all of this derivation, and you get basically the eigenvalue up to machine precision. So it actually has a very strong correlation. But maybe we can go back to that later. So I'm drawing a network. I choose a node V with probability depending on its x degree. And to increase localization as much as possible, I'm going to connect to the neighbors of the chosen node with largest degree. Why? Because if I have a node and I want to increase localization around it, if that node has a neighbor of large degree, then I want to continue increasing that degree so that it's more and more localized, right? So I'm going to choose a node and connect to the neighbors, to its neighbors of largest degree. Now I want a little bit of sorry. Let me say that this second step is sort of reminiscent of the copying model, because I'm choosing a node in the network, and instead of connecting to it, I'm connecting to a neighbor, right? Now I want to add a little bit of variance to this thing. So instead of connecting to the neighbors of largest degree, I'm going to connect to the neighbors with probabilities depending on their degree. And because I want to use x degree to tune the amount of localization that I find, I'm going to add this parameter beta here. So all of this is just to say the following. I have a hypothesis that x degree can tune the amount of localization. And what this growth model allows me to say is that for for positive values of beta, I should see a localized eigenvector. For negative values of beta, I should see a delocalized eigenvector. And we know how to measure this using the IPR. So I coded this up like 2 weeks ago, and it actually works, to my surprise, because so these are some experiments. Sorry. Here you have the size of the network. Here is the IPR of the non-backtracking principal eigenvector. This should be R. So this is adding 10 edges at a time to the network. Red lines correspond to positive values of beta, which after a little bit seem to be leveling off to a constant, which means a localized eigenvector. Blue lines are negative values, which are very much decreasing with the size of the network. The gray line is for beta equal to 0. Beta equals to 0, meaning choosing the neighbors in the second step uniformly at random. So that's what I wanted to see. It's great. It's beautiful. I don't know what to do with it. To be completely honest, like I said, this is a work in progress. I know there's something here. I know that these two quantities are correlated. The point is, what else can we say? So what are the consequences, right? Like now I can generate random graphs that have a localized eigenvector. What does that mean in terms of percolation or epidemic thresholds, and so on? So I'm going to skip on a couple of slides because I'm running out of time. I just wanted to say there's many open questions for this second part. For example, well, like I said, what happens with the epidemic and percolation thresholds? I am very much a mathematician at heart, so I would very much like to rigorously prove that these networks actually, with high probability, generate a localized eigenvector. Though, like I said, this is a non-symmetric matrix, so trying to do that sounds hard, perhaps even impossible. So real quick, a summary of the entire talk. First of all, first take-home message: non-backtracking matrix B is awesome. You should look into it. It's great. Has a lot of applications. It's very hard to analyze. 2, epidemic threshold SIR model can be approximated by 1 over the leading eigenvalue of the non-backtracking matrix. The drop in the eigenvalue when you remove a node is correlated to the X-centralities, X non-backtracking centrality or the X degree centrality. Normalized X degree is the same as 1 minus the inverse participation ratio of the square of the X's degrees of my neighbors. And growing a graph by optimizing for X degree leads to a localized non-backtracking eigenvector. there is much more to say, but I would like to leave some time for questions. You have some links here. The first one is the main paper. There's some code out, and remember I said that there are some terms that I'm neglecting in these derivations. Well, the point is that this is so hard. Analyzing this matrix is so difficult that we weren't even able to bound those terms for the first paper, the first time around. I had to write an entire different paper to rigorously prove that those terms are small. And even in that case, there's a whole wide gap of things that still need to be done. So this is sort of like the mathy, the gory math behind it. So let me just acknowledge my collaborators, Kevin Chan from the Army Research Lab, Han Tong from University of Illinois at Urbana-Champaign, and my former advisor, Tina Elias-Rad. So thank you very much.
So thank you very much. Do you have any questions in the room? Oh, yes, please.
I'm sorry, I really can't hear anything right now.
Okay.
Can you maybe try again? Or no, I can't hear you.
Me?
So I can hear you better, but it's very like you're coming in and out.
Can you hear me better now?
Yes, you have kind of like a robot-like voice, but I think I can hear you. I'm sorry, I can't hear anything. Yeah, I think it would be better if somebody wrote the question in the chat. That's perhaps because the sound is even worse than before. Sorry.
Can you hear me?
Yes.
Okay. Yeah, thanks for a great talk. I kind of wanted to go back to my question that I started to ask. Again, sorry for interrupting you. But kind of my question is, so you're truncating the series when you're approximating the determinant, if I remember correctly.
Kind of. It's not a series because the determinant is a polynomial, right? So it's a finite thing.
Oh, sorry. I thought you said you were neglecting other terms.
I am neglecting other terms, but it's a finite number of terms, I guess.
Okay. So I guess my question was, so I was trying to think about the correlation between this gap in the eigenvalues. And so I was curious if you could talk about any other structural effects, like say assortative mixing, different things, like some networks seem to do really well, others, yeah.
I would love to have a better answer. The question, the answer is I don't know. So I guess I would have to like try to measure the correlation of, I don't know, the local clustering coefficient of the removed node and how it affects the eigenvalue or something like that. That is very much hidden in those terms that I neglected. But at this point, I wouldn't be able to tell you exactly how much, you know. I will say though that in the paper, some of the random graphs that we tried have non-trivial clustering coefficients, for example, in the particular case of clustering coefficients. And the approximation even in those cases seems to be really good. Other than that, I really don't know. The point is, like I said, getting the first term is hard enough to even try to say anything about how the other terms depend on the structure of the graph.
Cool. Thank you. Thanks for a great talk.
Yeah. So there's another talk in the another question in the chat says, does deleting a node always increase the threshold, or could it also decrease? Yeah. So the threshold always increases, which is the same. The threshold always increases, which is the same as saying that the eigenvalue always decreases. And in fact, so proving that the eigenvalue always decreases is not difficult. Trying to bound by how much is literally the last the recent preprint I had uploaded. There's some theory applying for non-negative matrices, right? Like Perron-Frobenius theory, for example, that will more or less tell you that if you remove a node or remove an edge, then the leading eigenvalue always behaves the way that it should. But that's pretty much it. It doesn't give you by how much, right? So you need other bounds for that. The only caveat there is, like I was saying at the beginning, is that if you remove a node of degree 1, then the eigenvalue doesn't move at all, because the non-zero eigenvalues do not depend on the nodes of degree 1. If you remove a node of degree 2 or more, then it always decreases. Yeah, thank you.
Do you have any questions? Or I don't see any questions. So, can you hear me now? Is it works? Yeah. So,
All right, thank you.